Hello everyone, welcome back to this online class. Today we are going to look at numerical solution of ordinary differential equations, and in particular we are going to look at Picard's method of successive approximations. So we have this question. We are asked to use Picard's method of successive approximations to solve the initial value problem given by dy over dx is equals to x plus y, subject to the condition that y of 0 is equals to 1. We need to find y of 0.3 correct to 4 decimal places. Now, remember, we are using Picard's method to approximate the solution of an ODE. And in particular, we need the value of y when x is 0.3. So if we look at our ODE and the initial condition, this one here is our f of xy, is f of xy. This 0 here is our x naught, and the one here is our y naught. So we can say here that our x naught is 0, y naught is equals to 1, and f of xy is equals to x plus y. So the Picard's method, or simply the iterative method, is that yn plus 1 as a function of x should be equal to y naught plus the integral from x naught to x of f of x yn as a function of x dx. So that is the iterative formula that we are going to be using to approximate the solution of the given initial value problem. And you can write here for n is equals to 0, 1, 2, 3, etc. So we are going to iterate until we achieve a convergence, or simply until the approximations, the successive approximations, converge to a constant value. So let's start. We need f of x, yn. So, and we know f of xy. So from here, let me bracket this. From here, it is clear that f of x, yn, which is a function of x, remember, will be equal to x plus yn. Where there is y, we replace that by yn, a function of x. So when I come to my formula here, we will now have this as y naught, and I know y naught to be equal to 1. So I'm replacing everything. Where we have y naught, we put 1, plus the integral. Our x naught is 0. We are integrating from 0 to x of x plus yn, which is a function of x. Integrate this with respect to x. Now the first approximation is y1 of x. That's when n is 0. So you can write here first approximation. First approximation. What we do here is to put n is equals to 0. Put n is equals to 0. So what we are going to get is that y1, a function of x, is equals to 1 plus the integral from 0 to x of x plus y naught of x dx. But we know y naught. Y naught is 1, so I'm going to replace it by 1. So what we're integrating is simply 1 plus the integral from 0 to x of x plus 1 dx. And when you integrate this, you're going to get, we have 1 plus x squared over 2 plus x. Remember here, the limits of integration is from 0 to x. So when you work it out, you're going to get 1 plus x squared over 2. You see, it is a function of x. So we need the value at x is equals to 0.3. So from here, you can just say that therefore, our y1, the first approximation, when x is 0.3, is equals to 1 plus 0.3 plus 0.3 squared over 2. And when you press that in your calculator, you need to get 1.3450. 1.3450. So proceed to find the second approximation. You see, we want to know whether this approximation will converge to a constant value. If not, continue iterating. So write second approximation. Second approximation. So what do? We put n is equals to 1. Put n is equals to 1. Of course, we are substituting it here in equation star. You can say in star. Even here in star. So what do we get? When n is 1, we'll now talk of y2. y2 as a function of x is equals to y naught is 1 plus the integral from 0 to x of x plus y1, which was a function of x, dx. And so this is the same as 1 plus the integral from 0 to x of x plus, what was our y1? We got it as 1 plus x squared over 2. 1 plus x squared over 2 dx, which is the same as writing 1 plus the integral from 0 to x. When I add those, I'm going to get 1 plus 2x plus x squared over 2. Integrate with respect to x. And so when you work it out, you need to get 1 plus, that integral will give us x plus x squared plus x cubed over 6. Remember, the limits are from 0 to x. And so when you plug in the limits of integration, we are going to get, and then you simplify, we are going to get 1 plus x squared plus x cubed over 6. So that is y2 as a function of x. Now let's evaluate that at x is equals to 0.3. So you can say, therefore, y2 when x is 0.3 Just substitute. That is 1 plus 0.3 plus 0.3 squared plus 0.3 cubed over 6. Press in a calculator. You need to get 1.3945. 1.3945. So that is the second approximation. You see, it's not the same as what we got in the first one. So we haven't achieved the convergence. So we proceed to the third approximation. So you write here, third approximation. What do? We substitute, or we put n is equals to 2 in equation star. Look at your equation star and substitute n is equals to 2. So that will give us y3 of x is equals to, let me write it here. So that is y3 as a function of x is equals to 1 plus the integral from 0 to x of x plus y2 as a function of x dx. And we know the expression for y2 as a function of x, so we can replace it, add it to x. y2 as a function of x plus x will give us this one. So this can be written now as 1 plus the integral from 0 to x of x plus y2. y2 was 1 plus x squared plus x cubed over 6 dx. And so when you simplify, this will give you 1 plus the integral from 0 to x of 1 plus 2x plus x squared plus x cubed over 6 dx. Upon integration, we are going to get 1 plus x squared plus x cubed over 3 plus x raised to 4 over 24. Limits are from 0 to x. And so when you plug in the limits of integration, you need to get 1 plus x squared plus x cubed over 3 plus x raised to 4 over 24. Now we want the value of the third approximation when x is 0.3. So you say therefore y3 when x is 0.3, you can substitute the value of x there. I don't need to write everything. When you substitute the value of x as 0.3, you need to get y3 to be 1.3993. Correct to 4dp. 3993. You see, we are almost achieving the convergence. We are almost there. So we proceed to the fourth approximation. When you talk of convergence, you simply look at these values, the ones that are bracketed. This one, this, and even the ones that we are going to calculate. You see now we are 1.3945. When you compare with y3, we get 1.3993. We are almost close to the exact, or simply the value Let's go to the fourth approximation. In this case, now we put n is equals to 3. Put n is equals to 3 in equation star. So when you substitute n is equals to 3, you're going to get y4 as a function of x is equals to 1 plus the integral from 0 to x of x plus y3 as a function of x dx. If you replace y3, because already we have it as a function of x, we are adding it to x, that will give us 1 plus the integral from 0 to x of x plus our y3 was 1 plus x squared plus x cubed over 3 plus x raised to 4 over 24 dx. Let me simplify that integral. So we'll have 1 plus the integral from 0 to x of 1 plus 2x plus x squared plus x cubed over 3 plus x raised to 4 over 24. Integrate this with respect to x. And so when you integrate, you need to get 1 plus that integral should give us x plus x squared plus x cubed over 3 plus x raised to 4 over 12 plus x raised to 5 over 120 from 0 to x. And so this will give us, if you plug in the limits of integration, you'll get 1 plus x squared plus x cubed over 3 plus x raised to 4 over 12 and then plus x raised to 5 over 120. So that is the fourth approximation. We want to know the value when x is 0.3. So you can say that therefore y4 when x is 0.3, where there is x, you put 0.3 and press in your calculator, you need to get 1.3997. 1.3997. Have we achieved a convergence? No, we haven't got to a constant value. So let's try the fifth approximation. So you can write here, fifth approximation. In this case, you need to substitute n is equals to 4. So I write put n is equals to 4 in equation star. So with n is equals to 4, we are going to get y5 as a function of x is equals to 1 plus the integral from 0 to x of x plus y4 as a function of x dx. So this should give us 1 plus the integral from 0 to x of x plus our y4 was 1 plus x squared plus x cubed over 3 plus x raised to 4 over 12 plus x raised to 5 over 120. Integrate with respect to x. If I simplify, we are going to get 1 plus the integral from 0 to x of 1 plus 2x plus x squared plus x cubed over 3 plus x raised to 4 over 12 plus x raised to 5 over 120 dx. And so when you integrate, what are we going to get? This will give us 1 plus, this integral is the same as x plus x squared plus x cubed over 3 plus x raised to 4 over 12 plus x raised to 5 over 60 plus x raised to 6 over 720. From 0 to x, plug in the limits of integration, you're going to get 1 plus x squared plus x cubed over 3 plus x raised to 4 over 12 plus x raised to 5 over 60 plus x raised to 6 over 720. So that's our y5 of x. Now we need the value when x is equals to 0.3. So you can say that therefore y5 when x is 0.3 is equals to, so you substitute x is 0.3 in this expression so that you get 1.3997, correct to 4 decimal places. 1.3997. That is correct to 4 decimal places. So the question is, have we achieved convergence? Yes. Look at the last two values at y4 of 0.3 and y5 of 0.3. It is a constant value. And so it means even if you proceed to the 6th approximation, 7th approximation, etc., you are going to get the same constant value. So this means that we stop here, and therefore, we can now say that therefore, let me use another color. So you can say since y4 of 0.3 is the same as y5 of 0.3, that is correct to 4 dp. And that result is, let me wrap this. That result is 1.3997. That is correct to 4 decimal places. Hence, it means that the value of y when x is 0.3 is equal to 1.3997, correct to 4 decimal places. So this is how to use Picard's method of successive approximations to solve a first order ODE. So thank you all for watching this video. Please subscribe to my YouTube channel. That is Professor Francis Okech. When you go to the YouTube search, type Francis Okech or Prof. Francis Okech, and you will find me right there. Also, don't forget to comment, like, and share this video. When we meet next time, we'll look at more problems involving numerical solution of ODEs. Bye-bye.